So let's look at Taylor series. And when we say Taylor series, we're talking about constructing a polynomial that has all the same characteristics of a function such that it's pretty much the same thing as the function, meaning it's a model. And so I know we already know sine x, but let's look at the function sine x. If you watched the previous video, you know the Taylor series expansion for sine x, and let's just pretend we don't, and let's build it from scratch. When I say we're going to build this thing, right, we're going to build it. And again, we're going to build it so that our polynomial and the function, such that we match all the characteristics. And so I guess I have to define what I mean by characteristics. A function has a y value, a derivative, a second derivative, a third derivative, and if I have all those exact same values, you could argue that you are essentially the same function. So let's go ahead and take the derivative of sine x. The derivative of sine x is cosine. The next derivative would be negative sine x. The third derivative would be negative cosine x. The fourth derivative, you start using Roman numerals, is going to be sine x. And the fifth derivative is cosine x. Now we have to decide where we're actually going to build this function. Let's again look at sine x. We'll put it down here. Sine x looks like this as a function. And what we're going to do is we're going to come up with a polynomial that has the same thing. Well, we've talked about this in class. The best polynomial, the easiest polynomial that has very similar characteristics of sine x is just y equals to x. And look at it, if you zoom in right here, the two functions really close to zero are almost identical. Now you could make the argument that you want to get better. Well, if you want to get better, then you have to add more terms. And if you think about adding a cubic term, it might look something like that, where the cubic function is a little bit better of a model to use around the origin than sine x is. And if you keep adding more and more terms, you keep adding a higher degree of accuracy to what our polynomial will be compared to the function. Okay, so let's build this thing. The polynomial we'll call p of x, and the first thing we want to do is we got to decide where we're going to build it. So if you look at our construction, we're going to have our center be at 0. Okay, so our center is x equals 0. And so let's figure out all of these values at 0. So sine of 0 is 0. Cosine of 0 is 1, 0, negative 1, 0. And this pattern is pretty easy. I'm just evaluating these things at x equals 0. So now we just need to come up with a polynomial that has these same characteristics, and then our polynomial will be the same thing as the function. And so we want our polynomial to have a y value of 0. Okay, that's easy. We just don't put a constant in there. And we want our polynomial to have a derivative of 1. Okay, let's use x. X has a derivative of 1. That's cool. It doesn't have any second derivative. Well, then we better not have an x squared term. If you had an x squared term and you took two derivatives, you'd have some factor there. And we don't want. We want it to be 0. So we got to skip the second derivative. The third derivative, we want it to be negative 1. So we know that x cubed is going to control the third derivative, right? If we take 3 power rules, we're going to get 3x squared, 6x, and then 6. And you're like, oh man, I don't want negative 6 to be it. I want it to be negative 1. And so we do this clever thing, and we divide by 3 factorial. The factorial compensates for the fact that we know we're going to create factors in the numerator from doing the power rule. And since we're going to get a 3, a 2, and a 1 from the derivatives, well, let's just go ahead and divide by 3 factorial, and then this will ensure that this factor becomes negative 1 after 3 derivatives. We don't want any fourth derivative, so skip x to the fourth, and then we want a fifth derivative of 1. Again, we know that if we divide by 5 factorial, this combination will give us a fifth derivative of 1, this will give us the third derivative of negative 1, and this gives us a derivative of 1, such that my polynomial has the exact same characteristics of this. Feel free to graph this and graph sine x. They're going to be really close. It's going to look something like this on your graphing calculator. And if we keep adding more terms, And how do we get more terms? Well, we got to keep taking derivatives, and we keep matching. We'll actually get an equal sign, right? But we don't really need all of these terms. Most of these terms are so small they don't really influence it much. Typically, we just need the first two, maybe the first three, and that's a really good polynomial that describes the behavior of sine as long as you're somewhere close to the center. And we can do this for all the functions. And if you look back on your Maclaurin series worksheet or watch the last video, this pattern exists for sine x, whether we build it or whether we just use the pattern. Okay, let's look at building e to the 2x. And again, we already know what the pattern for an exponential is. And I'll prove to you that it's the same thing if we build it. Okay, so then we look at our derivative. Our derivative is 2 e to the 2x. The second derivative is 4 e to the 2x again. We just keep getting a factor of 2. 8 e to the 2x, and we can stop there. And again, we want to match. So we want our polynomial to have the same characteristics. Let's center it at 0 still. So if it's centered at 0, this is just 1, 2, 4, and 8. I would make the argument that, okay, let's just match. We want our y value to be 1. Okay? We want the first derivative to be 2. Okay? That's pretty easy. 2x has a derivative of 2. Now, did the 2x mess up getting the 1? And you're like, oh no, because I'm still plugging in 0. So when I plug in 0, this goes away, and I still get a y value of 1 when x is 0. I still get a derivative of 2. And now I want a second derivative of 4. Plus 4 times x squared over 2 factorial. Look how easy that is. I know that when I take two derivatives, I'm going to get a 2 from the power rule, so I just divide by 2 factorial. They compensate, and I'm left with 4. Plus 8 times x cubed over 3 factorial. Again, I know when I take 3 derivatives, I'm going to get a 3 and a 2, so I cancel them with the 3 factorial, and I know I have a third derivative of 8. Now let's compare. We already knew from our pattern that e to the x was this function. We already knew that. And if we use the pattern idea, that says that we can just take 2x and plug it in for where we see x. So take 2x and put it in for 1. All right, we still get 1. Take 2x and put it in for the x, and we get 2x. Take 2x and put it in here, we get 2x squared over 2 factorial plus 2x cubed over 3 factorial. And you can see that whether we use the pattern to figure out what e to the 2x is, or we actually build it from scratch, we get the exact same thing. Both of the ideas are really related. Again, this was constructing it from scratch, looking at the function and its derivatives, and then this is building it using the pattern. Both of them really rely on the fundamental principle that says if you want to build a polynomial, this is how it's built. Use the function value, use the derivative, use what you want the second derivative to be. And again, I'm always going to end up dividing now by the power, because I would need the factorial to compensate for the power rule. Otherwise, this wouldn't end up being the coefficient. Plus the third derivative of a, x minus a cubed over 3 factorial plus dot, dot, dot. And I can do that forever. The more terms you use, the better your approximation will be. All right, let's do an example where we actually we're building it, where we're centering it somewhere other than A. Okay, let's build it at a different spot. Okay. Let's look at a square root. And let's just take y equals the square root of x. So that's my function, and that's not a pattern you even know. It's not a pattern that I necessarily even have memorized. But I can take a derivative of this. I get this as my derivative, that's power rule. The second derivative is going to be, what, negative 1 over 4, x to the 3 halves. Third derivative is going to be, I have to bring a negative 3 halves down, so negative 3/8 x to the 5 halves. All right, let's build this at x equals 1, because that'll be easier. We could have done 4 or 9, anything we know the square root of wouldn't be too bad. Let's figure out those values. Those values are 1, 1/2, -1/4, and that shouldn't be a negative there, right? Because I brought the -3/2 down. Let's get rid of that. And so we have this. Now we want to build a polynomial. All right, so let's build it. We want our polynomial to have a function value at 1, 1. We want it to have a derivative of 1/2 plus 1/2. And you're like, oh, wait a second. If I just put an x here, what's going to happen? Does this have a derivative of 1/2? Sure. But this doesn't have a y value of 1 anymore when x equals 1. Because if I plug in 1 here, I get 3/2. And I need to get 1. And so you're like, oh, right, let's just do a quick horizontal shift. And hopefully from the last sheet, you can see where this x minus a comes in. We have to center it at 1. Because this still has a derivative of 1/2, and it still has a y value of 1. I want it to have a second derivative of 1/4. Okay. X minus 1 squared over 2 factorial. When I take two derivatives, I'm just going to get this -1/4. And then plus 3/8 x minus 1 cubed over 3 factorial. This coefficient will always be the coefficient that survives, because this 3 from the power rule will end up being a 3 factorial, and that factorial and that will cancel. And then this polynomial has the same as this. And if you graph them, you'd see that. This looks like this. And if you graph this thing, it would be something, I don't know, it's some cubic function that's going to be super similar to this. So it's going to come down here. So there's 1. So it would be some cubic function that would look like that. And as long as you're around the value, x equals 1, right? We build it at 1. It's perfect at 1. And as you get further away, either this way or this way, it doesn't get as good. Again, that's how you construct a Taylor normal polynomial. And you have to talk about order, right? Order and degree, all those words we'll talk about, and the number of terms we use. But basically the problem has to tell you, use the second order. Right there. That would be the second order polynomial. Now, how many terms is that? Well, it's three terms. 1, 2, 3. 3 things. So they say use the first 3 terms. There you go. If they use the second order, same thing. If they said use the first 4 terms, well, then it'd be all 4 the blue I have. If they said do a linear approximation, well, then only be the first 2 terms, right? That's a line. First order and a line are the same thing. And again, we'll continue to discuss this in class, but hopefully this video gave you an idea of how to construct a Taylor polynomial that approximates the function.